Okay, start looking at worksheet 4. Okay, so number one, this one is starting off with Rolle's theorem. If here's my function, x squared minus 6x over x plus 2. Does Rolle's theorem apply to the function on the interval from 0 to 6? If yes, find the value of c defined by Rolle's theorem. So Rolle's theorem is trying to guarantee a slope 0. So there's a couple of things that needs to happen. We need to check to see, is the function continuous on the closed interval? Is the function differentiable on the open interval? But really, just have to worry about continuity. If I can show that the function is continuous on the closed interval, then it will the functions that I give you will be differentiable along the interval as well. The third condition is that the endpoints have to have this to share the same y value, so that this can happen. So I can draw a horizontal line between the two endpoints, which must mean that somewhere between there has to be a slope 0, and I'm looking for that location by using the derivative, basically looking for the critical point that's going to live between my endpoints. So we do have to worry about a potential continuity issue because we see a variable in the denominator. So okay, we set that denominator equal to 0. And we do see that there is a vertical asymptote at x equals -2. This is a break in the graph, but is this break going to interfere with my interval? No, so we're safe, right? So we know that this is the only issue over the entirety of the whole graph, and that issue is not disrupting my interval. So I know my function is continuous on closed interval. Make sure that you are checking it and that you are also writing out those conditions. Now, I did not do it perfectly right on the key. I have to make sure I write out both statements. And continuity is with brackets. Differentiable is with parentheses. Next up, I have to see what's happening at the endpoints, just like how I'm going to approach mean value theorem. I'm going to figure out what is f of 0 and f of 6. And we know that 0 over non-zero is a real number, fetches 0. Zero over 8, that is also 0. The two endpoints are the same, but if you want to just go through the same steps as mean value theorem, you can also do that. Change in y over change in x. So this confirms that the slope between the endpoints is 0 because the y values are the same. These don't have to be 0. They just have to be the same. Oh, I just thought of something that I see some students do. Let's say f of 0 ended up giving you 2, and f of 6 ended up giving you 2. Mean value theorem works, but am I going to set f prime equal to 0, or am I setting f prime equal to 2? 2. To 0. Okay. Back to 0. These numbers are the same, but I'm still looking for the slope between the endpoints. It's still 2 minus 2 over 6 minus 0, which is, 2 minus 2 over 6 minus 0, which is 0 over 6. So that's 0. Right, so you're always setting f prime equal to 0 because you're not setting it equal to the location. You're setting equal to the slope between the endpoints. So just want to point out, I realize that's something that I've seen in the past where some students set the f prime equal to 2 or 3. They know this Rolle's theorem, but they're not setting it equal to the fact that they're the slope value. Okay, that's what we need to do. We need to set f prime equal to the slope value, because even if these were order pairs that were at 6, 2, and 4, 2, this is still a slope 0. It's not a slope 2 or slope 4, right? Okay. Okay, next up, we have our average rate of change. And we have to set f prime equal to the average rate of change. But to get to f prime, I have to go through what? Derivative. What rule do we use? Quotient rule. Okay. Leave the denominator alone. You're really just working on trying to get that numerator cleaned up. Two x squared plus 4x minus 6x. It's negative 2x minus 12 minus x squared plus 6x. So 2x squared minus x squared is x squared, plus 4x minus 12, all over x plus 2 squared. Okay, so I have my average rate of change, my average rate of change and my instantaneous rate of change. So Rolle's theorem, you're always setting f prime equal to 0. If I'm setting f prime equal to 0 and there's numerator and denominator involved, do I set both equal to 0? What am I looking at? What are you looking at when you have this? Just the what? Just the numerator. Okay, the denominator, if you set the denominator equal to 0, then you're looking for places where the slope is undefined. right? What is going to cause the derivative to be zero in the denominator? That's not slope zero. That's a sharp turn or vertical asymptote or a hole. We're looking for slope zero, something like one of these points, right? Horizontal tangents. That's only going to come from the numerator of your derivative. I mean, you could also do 0/1, cross multiply, and that will also force just the numerator to be equal to 0. Okay, multiplies to be -12, adds up to be 4. X plus 6, x minus 2. So there's two places where slope is 0, at -6 and at 2. But are both of these valid for our problem? Okay. Just what? 2. Just a 2. The -6 is outside the interval, right? So just at 2. Our interval is from 0 to 6.
Wouldn't it be +6, -2, since it's positive 4x?
Well, when I factor, is it not true that I get an x plus 6 and x minus 2?
Oh, wait, yeah, never mind, never mind.
Yeah, so my factor is x plus 6, x minus 2, but when I solve, I'm going to have to change the signs. Okay, number 2. Number 2 is very much the same. It's mean value theorem. So we're going to go through the same process, continuity, differentiability. We're still going to find the endpoints, but chances are with mean value theorem, these are not going to be the same y values. So we have to find the average rate of change by finding slope. Okay, mean value theorem. We have to pay attention to the fact that our condition may be an issue. So if there's a denominator variable, we have to consider that and set that equal to 0 and see if that break in the graph is causing an issue with my interval. There is a break at 0, but that 0 is not going to interfere with my interval because that break is outside my interval. So I know my graph is going to be continuous on the closed interval. Okay, so don't do derivative yet, right? We're going to take the endpoints, plug it into the function, get our average rate of change first. Okay, take your endpoints, find your average rate of change. So the slope between the endpoints ends up being -1. Set that off to the side. Find the derivative. Now we could go through, we'll go through quotient rule here. Quotient rule here for 2. We have our derivative, which represents our instantaneous rate of change. We have our slope, which represents the average rate of change. Set these equal to each other and solve for x. If you want to cross multiply, you can. Divide both sides by -1. Take the square root. What's going to happen when we take the square root? Positive and negative, right? Plus or minus 1. So there's 2 solutions here, or 2 locations where we can expect a slope of -1 on the graph at 1 and at -1. But are both of these going to fit inside my interval? Just the 1. -1 is out. So our x value solution, we labeled it as our C. So when x is 1, this graph is going to have, at that exact moment in time, it's going to have a slope of -1. Because that's a guarantee, because the slope between the endpoints is showing the slope of -1 as well. Okay, number 3. Okay. Okay, number 3, use second derivative test. So remember, second derivative test, this is not a test for concavity. This is not going to find concave up, concave down point of inflection. This is an alternate way of finding relative max and relative min. So initially, it's going to feel like the same steps as first derivative test. We're still going to find f prime, set f prime equal to 0, find your critical points. But rather than using the sign line from f prime, we're going to plug into the second derivative function. That 6 drops out to be 0. Factor out the x squared. Set both equal to 0. So these are our candidates for relative max, relative min. We'll set these off to the side because we're not going to do a sign line here. So now we're going to bring out the second derivative function. That's where the name is coming from. It's the fact that we're using the second derivative function to help decide what's happening at these points. So moving on to the second derivative, this is my f prime or y prime. Second derivative becomes 3x squared minus 12x. Okay. Are we going to set this equal to 0? We would if we were trying to find test for concavity, right? But we're not finding critical points here. We're using this as a tool to determine if these are max or mins. So you don't want to set this equal to 0. If you do, then you're doing something else. That's test for concavity. So you're going to insert these critical points into y double prime. Does that make sense? Okay. So let's do y double prime of 0. Now this is a little strange here. What are we getting as a result? 0. Is this either, is this concave up or concave down? Neither, right? So this one tells us, okay, I can't tell what the curvature is looking like, so I can't really know what's happening here. So this tells us that our test is inconclusive. Meaning that if we really wanted to find out what's going on at 0, we would have to go through our f prime sign line and actually see if there's a change in sign to tell if it's a relative max, relative min. But it's possible that it's probably neither. It's probably just a horizontal slope without a max or a min. But we don't know. Okay, y double prime of 6. Okay. We'll test our other candidates. So 3 times 36 is 108. 12 times 6 is 72. 108 minus 72 is 36. Now, what is this number telling us? The number is not that important. It's positive, right? So positive second derivative means concave up. Concave up looks like this, which must mean that this point is a what? Relative min. But many students will call this a relative max because they see a positive number, they associate a positive number with a larger value, so they assume relative max, but that's the wrong conclusion. That number is not a location, that's a curvature value. That curvature value tells us the graph is part of this is part of a concave up graph. Relative minimum is there, not relative max. So don't include that 36 in your justification. You can just say relative min at x equals 6. If I wanted to find the y value, I would have to plug the 6 back into the original function. This is not my y value. It's not 36. This is only used to help us determine whether it's concave up or concave down, and then we can determine its relative minimum. Sorry, yeah, concave or concave down, and then from there, we can look at the graph to tell whether it's relative max, relative min. Let me give you an alternate example of second derivative test. Let's say I had f of 2 is equal to -5, f prime of 2 is equal to 0, and f double prime of 2 is equal to -108. Okay, so this gives us location, this gives us the slope at 2, and this gives us the curvature value at 2. So you don't have to sketch it out, but you could. The order pair is at 2, -5. Slope is 0. So slope 0, it could be, looks like this. Could be a horizontal tangent here, horizontal tangent here, horizontal tangent here. So it could be slope 0, part of relative max, relative min, or neither, but we don't know, right? We don't know which of these options it is. And we're relying on this to tell us what's happening. So what does that -108 tell us? Good, concave down, therefore what? Max. Relative max, yeah. I know it's confusing, right? That -108 feels like such a small number. It should be a relative minimum if that's a order pair, but this is not order pair, that's a curvature value. So there's a relative max at x equals 2. We can actually know what the order pair is, right? Relative max at 2 -5, because we have the order pair there. Okay. You can understand why students want to make the wrong conclusion, because that number kind of throws us off a bit, right? Okay, let's look at a graphing problem. Okay, sketch a graph with the following characteristics. I can gather information about the order pair by looking at the first part A here. So I'm just going to plot those points. That's done. Second statement, f prime is greater than 0 if x is less than -1 and if x is greater than 2. What does f prime greater than 0 mean? Another way of saying that is what? What's another way of saying f prime is greater than 0? Right. Well, that would be f of x greater than 0, right? This is, well, it says f prime, right? Yeah, f prime. What's f prime talking about? Slope. Right. F prime is slope. Derivative, f prime. That's, if those words feel very abstract, but if we can say the word slope, it makes it more concrete, right? Slope greater than 0, that means what? Positive slope. Right? That means the graph is rising. Where's the graph rising? Okay, what's another way of saying less than -1? In which direction? To the left. Yeah, to the left of -1. And x is greater than 2, that means to the which direction? to the right of 2. So positive slope to the left of -1 and to the right of 2. Okay. Are we okay with this process? Are you able to look at that statement and convert it into something that is a visual um, demonstrate that visually on a sign line? Because if you can do that, then it's a lot easier to sketch your graph, right? Because you know how your graph is going to move. Okay, f prime of x is less than 0 if -1 is less than x is less than 2. What does that mean? F prime less than 0 means what? Negative what? Slope. So graph is falling in this middle interval. Okay, part D, there's a point of inflection at 0.12, so that's another order pair that we can put onto our graph. Took care of A, B, C, and D. We just have E and F left. F double prime of x is less than 0 if x is less than 1. What's another way of saying f double prime is less than 0? What does that tell us about the graph? Concave down. Okay, where's the graph concave down? To the left of 1. F double prime of x is greater than 0 if x is greater than 1. Wave up to the right of 1. Okay, so focus on your f prime sign line first, because this will kind of just help you map out your graph without having to worry about your curvature. And then we can go back and retrace the graph with the appropriate curvature. But right now, we know our graph is going to be rising, falling, rising again. Okay, we expect a relative maximum at -1. We expect a relative minimum at x equals 2. And then we know our graph is basically, this is it. It's just, it's not as clear as it could be in terms of curvature, but we know this is the movement of the graph, right? It's gonna, so we're not, even after we do our curvature adjustments, it's not gonna veer too far from this path. We're still gonna rise, fall, and rise. So concave down on this first interval up till 1. And then it's after that point of inflection, that concave down is going to change to a concave up. And there's our sketch. Okay, number 5, extreme value theorem, because we're trying to find the absolute max and absolute min. There's only one condition for extreme value theorem, and what's that? Yeah, just continuity, right? So we look at the fact that there is a denominator, so we have to consider maybe there's an issue, maybe there's a vertical asymptote. So we set x squared plus 4 equal to 0, see if we can find any vertical asymptotes. But we end up with something that is not a real number, which tells us that there is no real number that will cause the denominator to be 0, which means that there's no vertical asymptotes, right? Even though there's a variable in the denominator, nothing that I can plug in for x will cause my denominator to ever be equal to 0, because if I solve for x, I'm getting an imaginary number. So no vertical asymptote, which means that there is no disruption with my interval. My function is continuous on the closed interval, but we have to make sure we state that condition. Okay, next up, we know that if we're trying to find absolute max or absolute min on a closed interval, we know we have a couple of candidates to consider, right? We know we're going to test endpoints, but there could be critical points that show up as well. So how do we find critical points? Find what? Yeah, derivative, and set the derivative equal to 0. Numerator and denominator, assuming that there is a denominator in our derivative. Okay, leave the denominator alone. You're just cleaning up your numerator. Okay, what do I do with this derivative here? Okay, which part? Both. So I do want to start pointing out, maybe some confusion students may experience is, wait, when do I set the numerator equal to 0? When do I not set the denominator equal to 0? If you're trying to find critical points or extreme value theorem, you're going to set both numerator and denominator equal to 0. But if it's Rolle's theorem, you're trying to guarantee a slope 0. So if there's a denominator in your derivative, you ignore it. You're setting the numerator equal to 0 because you're not looking for sharp turns. You're looking for slope zeros. So, so yeah, maybe that is throwing some of us off because it's like, wait, when do I set the numerator? Like it feels like arbitrary, right? But Rolle's theorem is looking for slope 0. So you're only setting the numerator of your derivative equal to 0. But critical points, we could be looking for sharp turns. So sharp turns can come from the denominator of the derivative. So we need to also consider the denominator. Now the numerator is going to just give us 0 if I divide both sides by 16. Here, if I take the square root, I'm still left with the same issue where no real numbers here. Just like before when I set the denominator equal to 0, I'm not getting any critical point here because these are all imaginary numbers. So how many points am I going to test with as candidates? 3. I have one critical point that lands inside the interval. This one I can keep. And I have 2 endpoints that I'm always testing 2 endpoints. So my minimum for extreme value theorem, assuming it passes the continuity condition, is always 2 candidates. And I may have more than 2, and this one is a valid candidate for my critical points. So I have 3 to test. And how do I test my endpoints and critical point? Into the original, yeah. So I have the results from my endpoints, and I'm going to make my conclusion just based off of those numbers. What's the highest number that you see? Okay. What's the highest y value? 3/5. That's your absolute max. What's your lowest y value? That's your absolute min, right? So you can say absolute max value is 3/5 because that's the highest y value. You don't have to give me the x value, just give me the y value. If you want, you can say at x equals -4 and 4, or absolute min value at x equals 0, but you don't have to. Okay, I'm looking for the y values. And make sure that you don't give me ordered pairs. Then I'll take off a point because then you're putting equal weight with the x and y. I want the weight to be on the y value. Okay, why don't we go back and do some problems from worksheet 2. Any questions with worksheet 4? Okay, worksheet 2, number 1, find critical points. So we just set g prime, find g prime. And if there's a numerator and denominator, then we'll have to set both numerator and denominator equal to 0 separately, right? Okay, I'm getting my radical term ready for power rule by converting it into a rational exponent. Do some cleanup here. 16 and 2 becomes 8. I could push that x down to the denominator. And you can tell that, okay, these are not sharing the same common denominator. So let's push the, let's create common denominators so that we can cause these two separate fractions to merge together. And once it merges together, we can look for critical points in both the numerator and denominator. Okay, so what's my common denominator here? We look to balance each of our fractions here. So this denominator has not changed to get to the new denominator. So if there's no changes below, then there's no changes above. Here, my denominator is different than my new denominator. I'll have to multiply 1 by x to the 1/2 to reach that new denominator. So that's what I need to do with the numerator as well. You multiply the top by x to the 1/2. So 2x times x to the 1/2. If I multiply x's, I add the exponents. So 1 plus 1/2 is 3/2. So this allows me to create one fraction now that I have a shared denominator. Set both the numerator equal to 0 and the denominator equal to 0 separately. This one's easy, square both sides. I'm still left with x equals 0. This one. Divide both sides by -2 first. The way I can undo that power to the 3/2, I can raise both sides to the reciprocal power. Because then I can get the 3/2 and 2/3 to go away, right? Because 6/6 is 1, so that allows me to transfer that exponent to the other side. And then 4 to the 2/3 is just that number. You can make it cube root of 16, or you can leave it in that form. And so we have 2 critical points, right? Number 2 is another extreme value theorem. Maybe we can skip that one. Let's do another graphing one. So this is on page 6, number 8, sketching a graph. Page 6, bottom of the page. Okay, so starts off easy, order pairs. We just plot all those points onto our graph. First few statements are all involving f prime, so I can put that information onto my f prime sign line. Okay, first up, f prime of x is less than 0 for x is less than 2 or x is greater than 4. So let's verbalize this again. What does that mean? F prime of x is less than 0. Negative slope. Slope. Negative. Okay, where is my slope going to be negative? Yes. Because why? Yeah, so here f prime of x less than 0, where's slope going to be negative? Left of 2 and or to the right of 4. Okay, everybody good with that? Okay, next statement. F prime of 2 does not exist. What does that mean? That again? Well, we can't really say it's asymptote because the point does exist. You see that 2, 0. In this case, point does exist. But can you phrase it a different way? F prime of 2 doesn't exist. What is that? The slope at 2 does not exist. So what do you think that could be then? All right, it's a sharp turn. Okay. The slope at 2 does not exist. F prime of 4 equal to 0. What does that mean? Slope at 4 is 0. So this slope does exist, right? But we know it's going to be a smooth curve here. f prime of x is greater than 0 for 2 is less than x is less than 4. Positive slope between 2 and 4. Good. Okay, last statement is telling us about the second derivative sign line. F double prime of x is less than 0 or x doesn't equal to 2. What does that mean? Good. Concave down everywhere but 2. So the only place the graph is not concave down is when x is equal to 2. Okay, let's focus on the first derivative sign line first, because we don't want to do this first. If we do this first, we may end up conflicting with the property that needs to stand for f prime. So this will kind of help us map our graph so that we're not veering too far from the true graph. So we know the graph is going to be decreasing up until 2. And what do we want to happen at 2? There's a relative min, but the graph has to look a certain way. It needs to have a what? Sharp turn. And right now, I'm going to not worry too much about it. I'm just doing a negative slope. A relative min at 2 is going to rise to some slope 0 at 4, and it's going to fall again. So this is the path of my graph. No matter what I do with concavity, I'm not going to cause I'm not going to add any new path to it. Okay, I'm already following the path that's already been laid out. So I want my graph to be decreasing up until 2, but I want my graph to have what type of curvature here? Concave down. So all the meanwhile, you want to graph it in a way that causes a sharp turn at 2. And then what's going to happen after 2? My graph is going to still maintain what? Concave down. Now this feels like a full concave down shape, but this doesn't quite feel like it. So can I do this? Can I just make it so that my graph has a more of a full concave down shape? Why can I not do this? Because my slope has to be what? Negative, right? It has to be negative all the way from negative infinity to negative 2. So if I include a full concave down, then I'm creating a positive slope, which we know is not true because that's not what the property tells us. So I just want to point that out because it's going to be tempting. It's going to be tempting to do that because we see this shape and we feel like we have to do a full concave down, but we don't. We just have to make sure that the path within our grasp has that curvature, and that's enough, right? So we're not going to include anything past. We're still going to maintain that our graph is going to be decreasing all the way through here. Okay. I didn't go over first derivative test. I didn't go over test for concavity. I feel like those you guys know how to do. I just wanted to focus on the ones that are more involved, more complicated. Okay, let me know if you have any individual questions. All right, thanks.